So, it is very interesting to understand this rest mass energy concept. Normally in non-Newtonian mechanics, when we talk of energy, we talk of only mechanical energy, kinetic energy plus some potential energy because of some interactions. But what goes inside that object, that we are not concerned with, or we do not address that question. But in relativity, that is also addressed when we say rest mass energy, and it is an object. So, you have a large number of atoms, molecules, ions, all those things, electrons. So, all those smaller particles inside that object, they are also in random thermal motion, and then the molecular interactions are there. So, that whole energy together with the rest mass energy of all those particles themselves, that whole energy is included in rest mass energy. And therefore, rest mass of an object is not very specific about that object. If you change the configuration of the internal configuration of that object, rest mass can change. So, we talked about an object which is at a lower temperature, and the same object without any phase change, etc. The same object we heat slightly, we increase its temperature, the thermal motion increases inside that object, object is still at rest, and we say that its rest mass energy has increased, its rest mass has increased. So, a hotter body will have a higher rest mass than a colder body. Another example I gave, compressed spring and the spring in its natural lengths. So, both are at rest, but the rest masses are different. This compressed spring has more rest mass because the total energy is more. So, that is how that rest mass has to be understood. I gave several examples from nuclear physics and atomic physics. We said that this, if you have 4 protons, or let us say 1 proton and 1 neutron, and then make a nucleus out of it, which is called heavy hydrogen nucleus, right. So, hydrogen is just a proton, and heavy hydrogen nucleus we write like this. This is hydrogen nucleus, which is just a proton, which is nothing but just a proton, hydrogen nucleus. But that way to write a nucleus is like that. Here is the name, and this is the number of protons, and this is the total number of protons and neutrons. So, there is no neutron. So, the number of protons is same as the total number of protons, neutrons. We collectively call it nucleon. So, this is a hydrogen nucleus or proton, this is just a proton. And if you have this 1 proton together with 1 neutron, then this total number is 2. So, that is the nucleus of heavy hydrogen. So, this is nucleus of heavy hydrogen. It is called deuteron. So, this is proton and this is deuteron. In deuteron you have 1 proton and 1 neutron, but the mass of this deuteron, we also write it D, mass of this deuteron nucleus is less than mass of proton and plus mass of neutron. It contains 1 neutron and 1 proton, but still its mass is less than the sum of masses of these two, and the difference is about 2.2 mega electron volt per c square divided by c square. Mass is energy divided by c square. So, that is how things work. We have fission reactors, We have 21 fission reactors in India. The best ones are here only in terms of the operation, continuous operation, safety. Our 21 reactors are rated very high among the total 450 or so reactors in the world. So, in this what we do, we have some uranium nucleus, 236 uranium 92, right. We have 235, then we put neutron and we make this, and this breaks in another nuclei x plus y, and then some electrons etc., and then some neutrinos, and then that is all, then energy. So, when it breaks and you get this energy which is used to create electricity and all those things, but if you think of rest masses, the number of protons, the number of neutrons and number of particles, that rest mass is there, but then the rest mass of if the product is small, then the rest mass of this, and it is this difference delta m times c square, that is that energy which we obtained. So, in a way we have converted mass into energy, but we have not destroyed any particle. The protons are still there, neutrons are still there, electrons are still there. In the deuteron problem, if you make a deuteron, what you get? You start with a proton and a neutron and then combine and then do this. So, this mass from here I am making this deuteron d, and then some energy is available because this rest mass is small, this rest mass is more, and therefore, it gives me something like 2.2 MeV by c square, like that. So, this delta m times c square is that 2.2 MeV. So, if I am making a deuteron out of proton and neutron, I am reducing the rest mass, and that reduction in rest mass, that is made available in the form of energy which is 2.2 MeV. So, that kind of mass energy conversion goes on very regularly. You heat the object, you do a chemical reaction, and mass energy conversions are always there. But there is another kind of conversion of mass and energy with the same equation, delta E is delta m times c square, and that is the particles are absolutely destroyed. Here the particles are not destroyed. When I am making this nucleus, that d nucleus, the deuteron nucleus, the proton is still there, the neutron is still there, and here also you have one proton and one neutron. But now what I am talking is particle disappears and energy appears. So, mass has been converted into energy. So, I take specific example of electron, positron annihilation. Annihilation, they destroyed, they are annihilated, they disappear, they are no more. Electron you know very well, and positron is just antiparticle of electron. So, this positron, the only thing it is which is important for us at this time, that it's a something, an image of electron, you can say. Mass of this positron exactly mass of electron. Mass of positron is exactly the same as mass of electron. Then charge is plus E. Charge is plus E, same as that on proton. So, that is kind of, then there are many other things which are not important here in this discussion. So, these are called positrons. We do not see many positrons around, and that is precisely because the positrons can combine with electrons and annihilate each other. So, how do we get the positrons as such? So, you have sources for positrons, you can make sources. One very common source is sodium 22. You know, sodium has 11 protons, atomic number of sodium. If you recall that periodic table, you have in the first column you have sodium, hydrogen, lithium, then sodium. Z is 11. So, number of protons in the nucleus of a sodium atom is 11, and generally sodium that is available to us, for example, sodium chloride, our common salt which we use in kitchen. So, that sodium will have 12 neutrons together with 11 protons in the nucleus. But if you take out one neutron and start with this 22 11 sodium 22, that decays into, right, that is a radioactivity chapter, different, sometimes we can have a course on that, but then this decays, a proton converts into neutron, a proton converts into neutron. So, 11 protons becomes 10 protons, and 10 protons is that noble gas at the rightmost column of the periodic table, that is neon. So, this becomes neon 10, and of course, this is 22, because here you have 11 protons and 11 neutrons, and here you have 12 neutrons, because one of the protons has converted itself into a neutron. So, and then when proton converts into neutron, then you have another particle, and this is positron comes out, some neutrino and energy and so on. Okay, so, if you have this source which is available by scientific companies, then if you have some source here, let us say this is a source or some solution of this sodium 22 Cl, salt solution, but sodium is no more not sodium 23, it is sodium 22. So, from there all this reaction will take place and positrons will come out. So, you can have positrons in the laboratory. Now, this positron, if it combines with an electron, the positron is destroyed forever and the electron is also destroyed forever, and what you obtain are 2 gamma photons, electromagnetic waves. So, it is just energy, it is not matter, it is not material, and this is matter. So, this matter completely converts itself into energy, that is also possible, and then you have gamma plus gamma, 2 gamma photons. Okay. Why 2 gamma photons? If you have an electron, if you have a positron and they are just close to each other to start with, and this whole mass is converted into energy. How much is mass of an electron? Mass of electron and mass of positron both are 511 kilo electron volt by c square. So, when this mass converts into energy, how much energy you should get? The total mass is 1022 keV by c square, that is the mass which is converting into energy, and that mass into c square, this will be the energy, and that will be just 1022 keV. But you do not have 1 gamma with this energy, you have 2 gammas, 511, 511. Okay. So, this is 511. Now, this is energy, this I am writing energy. I do not write mass of a gamma particle, it is massless. This is 511 keV. If these positrons and electron, if these 2 particles have some initial motion, then it is possible that slight difference this and this, but the sum will still be 1022 keV. Why 2? Because of linear momentum. if you have this electron and this positron and they are just close to each other, not moving with any great velocity, the linear momentum is 0. Linear momentum is 0, and when they convert to energy, then the linear momentum must be conserved, it should remain 0. But we will talk in upcoming lectures that a photon also has momentum, energy and momentum. So, if this 1022 keV photon is to be created, and photon will always have some energy and some momentum, but we need 0 momentum because the initial momentum is 0. So, you cannot have just one photon to have this energy and 0 momentum, that is not possible. So, there are 2 photons going in opposite directions, one photon in one direction, one photon in opposite direction, and 511 keV energy here, 511 keV energy here. The momenta are also equal in magnitude, opposite in direction, and the total becomes 0. So, this is direct conversion of material into energy. The reverse is also possible. From the energy you can create material, you can create particles which never existed. So, this example itself can be taken, the reverse of this. If you have some kind of material here, generally in nuclear physics laboratories they have detectors, varieties of detectors, solid here and gamma ray comes here, and then there is some process by which it loses energy here and that is trapped, and from there we know what was the energy of the original gamma ray. So, if you have this kind of detector and if there is a gamma ray coming in with energy which is greater than this 1022 keV, then all that detection system detects photons which are this much less than the original energy. So, this energy has been lost somewhere, and then the detection system also detects photons of this energy 511 keV. 511 keV gamma rays are also detected. So, from this where this is coming, suppose your original is, let us say, something like 3022 keV. So, if you are getting something like 200 keV, if you are detecting these gamma rays, where are these gamma rays coming from? They are coming from the fact that this much energy out of this has been converted into electron and positron. A new electron has taken birth, a new positron has taken birth at the expense of 1022 keV out of this, and the reduced energy which is 2000 keV is that appears in the detection system. And also the electrons and positrons which are created here, they will be moving in some direction, and this positron will ultimately meet some electron of this material, detecting material, and there it will again annihilate each other, and 511 keV gamma rays will be created, and those are detected in the system. So, together with the 3022 keV, you also have these photons. Remember, it is all stream of photons which are coming. So, some of these original gamma rays which did not go through this mechanism, that they are also detected, but some of them which are going through this mechanism of creating a new electron and a positron, they will give me this energy and also this energy. So, that reverse is also possible. You have heard of that Large Hadron Collider where proton beams are collided against each other, and the energies are in tera electron volt, very high energy. So, this is the latest high energy collider, But before that also people had been working with collision of proton beams. So, it is possible that you have proton, then they are coming towards each other, they collide with high kinetic energy. So, initial energy of this proton is very high. The rest mass energy is something like 938 MeV. This is the rest mass energy of this particle. But then when we accelerate the particle, we can go much higher than this. We can go to giga electron volt and then tera electron volt. So, that kinetic energy, when they collide, part of that kinetic energy can convert into new particles. So, you can have P plus P equal to P plus new particle, maybe P plus N, a new proton, a new neutron, or a deuteron, or some gamma, the mesons, pions, pi plus, pi minus, these are also particles, these are called pions. Neutral pions are also there. So, the original protons are there and new particles have been created, and these new particles are created from that kinetic energy which they were having before the collision. So, that conversion of energy into mass and mass into energy is very much real, and in that sense that mass itself can be called a condensed form of energy. So, m into c square, mass into c square, rest mass into c square is the rest mass energy, and on top of it you can have kinetic energy, and then you can combine all those things. So, that is the interpretation of that famous equation E equal to mc square that you should keep in mind. So, now let me return to energy momentum 4 vectors. Let us have some more discussion on that. So, energy momentum 4 vector, you remember we write it as E by c, and this is your total energy, this E is total energy. And then Px, Py, Pz. So, this is energy momentum 4 vector, and you remember when we had this position 4 vector Ct x y z, position 4 vector. Now, these quantities have a very good combination which is invariant, and that is minus c square t square and plus x square plus y square plus z square. It is invariant quantity. Invariant means if you change the frame from S to S prime, this does not change, and we just called it magnitude of this vector. Just like in our normal 3-dimensional geometry, the magnitude of a vector, of course square of that, is x square plus y square plus z square, position vector. So, here for 4 vector we define a similar quantity, and that will be minus c square t square and then plus x square plus y square plus z square, and that quantity remains invariant. So, it is a kind of magnitude square of this vector. So, when you change frames, when you rotate frame in 3-dimensional geometry, the components change, x, y, z components change, but the length of the vector does not change. So, in that same spirit, when we are going from S to S prime, these components will change, but this quantity which is magnitude square will not change. And since the transformation of this 4 vector and this 4 vector are identical, that is why they are 4 vectors. That same matrix you have to write there. If you want that primed coordinates, you have to put a square matrix here, gamma minus beta gamma 0 0 minus beta gamma gamma 0 0 0 0 1 0 0 0 0 1, and this transformation, this is a Lorentz transformation essentially. So, that same transformation equation is valid for this 4 vector, and the same transformation matrix is applicable for this position 4 vector. Exactly same, this and this are exactly same. That is why they are called 4 vector. That is the definition of 4 vector. Anything that transforms according to this is a 4 vector, and therefore the magnitude square of this will also remain constant when you change the frame S to S prime, just like this. So, what is the magnitude square here? The magnitude square here is minus E by C square minus Ct square. Similarly, here minus E by C square, and then plus Px square plus Py square plus Pz square, just like this, plus x square plus y square plus z square. So, this plus Px square and plus Py square and plus Pz square is that length square, and this remains invariant. When you do Lorentz transformation, x, y, velocity components, and from there you can write the linear momentum and total energy and all those things. But without doing all that algebra, I can state that this quantity is going to remain constant, and this is magnitude of linear momentum square. Hence, it is E square minus P square C square is invariant. So, when you change frame, this will not change. And for one particle it does not change. Even if you have two particle system, particles are moving with respect to each other, or they are going, colliding, doing something. If you have a system of two particles, you can write what is the total energy of those two particles, E1 plus E2. You have two separate particles going with some velocity, this going with some velocity. What is the total energy of this system? Energy of this plus energy of this. And what is the total momentum? P. That is also you can write P1 plus P2. And if this EP is a 4 vector for first particle, and E2 P2 is a 4 vector for the second particle, and 2 4 vectors when you add remains a 4 vector, right. In our 3-dimensional geometry, if you have a vector, you have another vector, you add and you get a third vector. Similarly, here this total thing will also be a vector, 4 vector, and if they are 4 vector, this should be invariant. So, not only for one particle, even if you have several particles, and then you take total energy of all the particles together as capital E, and total linear momentum of all those particles taken together as that Px, Py, Pz, you will still have E square minus P square C square invariant. Okay. So, we will stop here, we will continue with this discussion next time.